The directions say to solve the differential equation by using an appropriate substitution. Let's take a look at number 1. Suppose we have the quantity x minus y dx plus x dy is equal to 0. So what we're going to do is we're going to let y equal u times x. dy is u dx plus x du. So making our substitution, we get the following. We get the quantity x minus ux dx plus x times the quantity u dx plus x du is equal to 0. If we expand, we get x dx minus ux dx plus xu dx plus x squared du is equal to 0. Now, notice how we have xu dx minus ux dx. That equals 0. So the second and third term end up canceling out. And what we're left with is x dx plus x squared du is equal to 0. And this is a separable differential equation. So that substitution turned this differential equation up here into a separable differential equation. So it's a very clever substitution. And so this is what we have so far. Now, x dx is equal to negative x squared du. Dividing both sides by negative x squared, we get negative 1 over x dx is equal to du. Integrating both sides, we get the integral of negative 1 over x dx is equal to the integral of du. So u equals negative natural log of the absolute value of x plus c. But remember y equals u times x. Solving for u, we get u equals y over x. So y over x is equal to negative natural log of the absolute value of x plus c, right here. And multiplying both sides by x, we're done. So y is equal to negative x times the natural log of the absolute value of x plus cx. In example 2, suppose we have the quantity y squared plus xy dx minus x squared dy is equal to 0. So what we're going to do is set y equal to ux. dy is u dx plus x du. Making our substitution, we get the quantity u squared x squared plus ux squared dx minus x squared times the quantity u dx plus x du is equal to 0. Expanding, we get u squared x squared dx plus ux squared dx minus x squared u dx minus x cubed du is equal to 0, right here. But ux squared dx minus x squared u dx is 0, so the second and third term cancel. So what we're left with is u squared x squared dx minus x cubed du is equal to 0. And this again, just like in example 1, is a separable differential equation. So I want the term that involves dx on one side and the term that involves du on the other side. And that's where we're getting u squared x squared dx is equal to x cubed du. And rewriting, we get 1 over x dx is equal to 1 over u squared du. Integrating both sides, we get the integral of 1 over x dx is equal to the integral of 1 over u squared du. So natural log of the absolute value of x plus c is equal to negative 1 over u. And notice how I wrote natural log of the absolute value of x plus c as natural log of the absolute value of x plus c divided by 1, because then I can take the reciprocal of both sides. And at the same time, I'm going to multiply both sides of the equation by -1. And when I do, I get the following. I get u is -1 over natural log of the absolute value of x plus c. But remember, y equals u times x. So u is equal to y over x. Substituting in, we get y over x is equal to -1 over natural log of the absolute value of x plus c. Multiplying both sides by x, we get y equals -x over natural log of the absolute value of x plus c. And that's example 2. In example 3, we have dy dx is equal to y minus x over y plus x. Rewriting this differential equation, we get the quantity y plus x dy is equal to the quantity y minus x dx. And just like in the first two examples, I'm going to set y equal to u times x. dy is u dx plus x du. Making my substitution, I get the quantity ux plus x times the quantity u dx plus x du is equal to the quantity ux minus x dx. If I expand out, I get u squared x dx plus ux squared du plus xu dx plus x squared du is equal to ux dx minus x dx. And so notice how I have an xu dx on the left side of the equation, and I have a ux dx on the right side of the equation. So those two terms will cancel, and what we're left with is the following. We get u squared x dx plus ux squared du plus x squared du is equal to -x dx. So I want all the terms that involve dx on one side of the equation and all the terms that involve du on the other side. And so on the second line, we have u squared x dx plus x dx is equal to -u squared, -ux squared du minus x squared du. So x times the quantity u squared plus 1 dx is equal to -x squared times u plus 1 du. And then rewriting, we get -1 over x dx is equal to u plus 1 over u squared plus 1 du. And so the integral of -1 over x dx is equal to the integral of u over u squared plus 1 over u squared plus 1 du. So I just split up the fraction on the right-hand side. So negative natural log of the absolute value of x plus c is equal to 1/2 the natural log of u squared plus 1 plus arctangent of u. But just like in the last two examples, we're given that y equals ux, so u equals y over x. Making my substitution in, we get negative natural log of the absolute value of x plus c is equal to 1/2 natural log of y squared over x squared plus 1 plus arctangent of y over x. And so the next two lines is a fair amount of algebra. And when this gets reduced, we should come up with the following. We're going to get c equals 1/2 natural log of x squared plus y squared plus arctangent of y over x. Let's take a look at example 4. Suppose we're given x dy dx is equal to y plus x squared minus y squared inside the radical. So another way to say that, let's say it this way. In example 4, suppose we're given x dy dx is equal to y plus the square root of x squared minus y squared, where x is greater than 0. So I'm going to rewrite this differential equation as x dy is equal to the quantity y plus the square root of x squared minus y squared dx. So again, just like in those previous 3 examples, I'm going to let y equal ux. dy is u dx plus x du. If I make my substitution, I get x times the quantity u dx plus x du is equal to ux plus the square root of x squared minus u squared x squared, that quantity dx. Expanding, we get xu dx plus x squared du is equal to ux dx plus the square root of, factoring out that x squared, we get the square root of x squared times 1 minus u squared dx. Well, essentially, I can cancel xu dx with ux dx. Those terms cancel, and what we're left with is x squared du is equal to x times the square root of 1 minus u squared dx. Now, remember, the square root of x squared is equal to x because if you look at the beginning, notice how I have the condition that x is greater than 0. So I don't have to worry about absolute values here. So if we look at this line here, we get x squared du is equal to x times the square root of 1 minus u squared dx. And if I rewrite this, I get 1 over the square root of 1 minus u squared du is equal to 1 over x dx. Integrating both sides, we get the integral of 1 over the square root of 1 minus u squared du is equal to the integral of 1 over x dx. So arc sine of u is equal to natural log of x plus c. And notice on the natural log of x, I don't put absolute value bars because, once again, in the beginning of the problem, we're given that x is greater than 0. So I don't have to worry about taking the natural log of a negative number. Now, solving for u, we get u equals sine of the natural log of x plus c. But remember, y equals u times x. So u equals y over x. So y over x is equal to sine of the natural log of x plus c. Multiplying by x, we get y equals x sine of the natural log of x plus c. And that'll do it for this video where we did 4 examples solving a DE by an appropriate substitution. Thank you.